What up, what up? I'm the math teacher Goat. Now we are on section 1.7, which is rational functions and end behavior. So we spent the first half of unit 1 talking about polynomials. Now we're moving on to rational functions, which is fractions. All right. Notes are in the description. Hit the like button, hit subscribe, leave a comment, tell me how much you love me. Stuff like that goes a long way. This is a full lesson. Download those notes and follow along. Please, thanks. First thing that we're going to do is we're going to solve this guy right here. Well, let's solve it by factoring. So we're going to say two numbers that add up to 1 and multiply out to -6 are going to be -2, +3. Okay, we're factoring that quadratic. Now we're going to use the zero product property, set each of these equal to 0. So x minus 2 equals 0, x plus 3 equals 0. And you're like, oh, all I have to do is add 2. So x equals 2 is one solution. And all I have to do is subtract 3. X equals -3 is a solution. And there you have it. Okay, so x equals 2 and x equals -3. Now, the way we're going to begin this lesson is we're essentially going to look at what we have here, but throw that in the denominator and graph that. So let's do Desmos for this one. Let's run to Desmos and graph that on Desmos and see what we see. All right, so this is what it's going to look like being graphed on Desmos. We have f of x equals 1 over 1 divided by, and then it was x squared plus x minus 6. Now, this is a rational function. Now, the question is what do you see? Well, if you remember in the previous problem, things seem to explode at -3 and 2. Our zeros were -3 and 2. When graphing these, we notice that we have this weird split of the graph at those exact numbers. All right, so when we deal with rational functions, what we're realizing is those numbers make the denominator equal to 0. And when you have a denominator of a fraction equal to 0, it is undefined at those moments. And we have little explosions that we're going to talk about what that means in a little bit. But that is graphing that function right there. All right, so what we noticed when we graphed this, okay, seeing the same exact numbers over here. All right, we had this weird thing where it went up like this and then kind of went down and then kind of did that. And we notice all of this action happened right here at -3 and here at +2. And again, the reason why it explodes like that is at 2, we plug it in and get 0. When we get 1 over 0, it's undefined, which means we're not going to have an answer at that moment. And so graphically, you see an explosion. Same thing with -3. At -3, you plug it in, you get 1 over 0, and another explosion is going to take place at -3. Okay? So explosions everywhere. Now, a rational function is when you have something like f of x over g of x, but keep in mind, you are not allowed to have a denominator equal to 0. So when that happens, g of x cannot equal 0. When that happens, your domain changes and you have numbers that are not in the domain. So looking at this guy graphically, if I were to backtrack, because the next thing right here is we're talking about domains. If I were to look at this right here, -3 is an x value that's not allowed. You're not allowed to use -3. You're also not allowed to use 2. So if I wanted to describe what's going on here graphically, our domain would be everything all the way up until -3. So negative infinity up until -3, but -3 is not allowed. So we cap it off with the parentheses because you're not including -3. Then -3 is skipped, and you pick back up at everything greater than -3 and go all the way up to 2. 2 is also skipped, so you union that, and you go from 2 to infinity. So some teachers might write this out differently. This is the domain. Basically, this is saying everything but -3 and everything but 2. You might have teachers that say x is just not allowed to equal -3 and 2, like that. And they might say all real numbers except x equals negative, x cannot equal -3 and 2. It all depends. But I'm going to use interval notation. Regardless, what I realize is any number that makes the denominator 0 is no longer in the domain, and therefore I have to skip it. So algebraically, what that looks like here is I need to figure out what makes the denominator equal to 0. The denominator is x cubed minus 9x equals 0. I can factor out an x and get x squared minus 9 equals 0. X squared minus 9 is difference of squares. So that's x times x minus 3, x plus 3 equals 0. So the numbers that make the denominator equal to 0 are 0 from the zero product property, positive 3, and negative 3. So I'm not allowed to use 0, 3, or negative 3. So when I write out the domain, my domain is going to be from negative infinity all the way up until negative 3, union. Then from negative 3 to 0, union. Then from 0 to 3, union. Then from 3 to infinity. Okay, this says all the way up and skip negative 3, all the way up and skip 0, all the way up and skip 3, gone. Now we have a graph, and it looks like we have the destruction happens right around this number right here. I'm going with that guy right there. So that number is -1, 2, 3, -4 is where we have an explosion take place. Everything else is good. All the way from the left until -4, and then it breaks up at -4 and then goes on forever. So this one is just from negative infinity to -4, union, -4 to infinity, and that's my domain for you. Okay? Great. All right, now, those awful explosions, what are they? Well, we're going to talk about two of them. The first one that we're going to talk about, and probably the only one I think we're going to talk about today, is called a horizontal asymptote. Now, you may have noticed from the one picture that I drew on Desmos that things seem to level out quite nicely. Okay, horizontal asymptotes are horizontal lines that the graph of the function approaches as x tends to infinity or negative infinity. Basically, it's going to flatten out at a horizontal line somewhere. Okay, whether it goes like this, whether it goes like this, or more common, goes like this, it's going to flatten out like that. What we see here is this green dashed line represents a line that neither of my graphs are actually going to ever hit. Okay, all the way to the left, it's going to flatten out and tend towards that line. And all the way to the right, it comes up here and tends towards the green line but never touches it. Horizontal asymptotes are constant flat lines, which means they're in the form y equals some number. So like this, if that was like 1, 2, 3, this would be the line y equals 3. Okay? Horizontal asymptotes. Horizontal asymptotes. Now, end behavior. When we state end behavior, we are stating it in limit notation. We know from polynomial functions that if things go up and to the right, the limit as x approaches infinity goes to the right, positive, infinity, vice versa. So what we're seeing here is we have the limit as x approaches negative infinity and the limit as x approaches positive infinity. Let's call this f of x. Let's give it a name. So the limit as x approaches negative infinity of f of x is asking, where is my arrow pointing as I move to the left? Well, as I move to the left, it's going down and to the left. So this is going down to negative infinity. So you are going to be negative infinity. The limit as x approaches positive infinity of f of x is asking, where is my graph going as I move to the right? And since this is going up and to the right, it's going up, which means it's going to infinity. Now with polynomials, whenever we did a problem like this, the answer was always going to be either infinity or negative infinity, because it was either always going up and to the right or down and to the right, or up and to the left or down and to the left. Now we have an issue where things start to flatten out. Okay? Now, sometimes these aren't so obvious, so what I'm going to do is I'm going to make believe that the horizontal asymptote is going to be this line right here. Probably could have stole a better graph from the internet, but we're going to make believe that the horizontal line asymptote is going to be right there. Now the limit as x approaches negative infinity, and let's call this g of x, is asking, where is this guy going as we move to the left? Well, as we move to the left, this red line is tending towards this blue line. It'll never touch it, but it'll get awfully close to it. So we are going to say that that blue line goes through -1 right here. Therefore, the limit as x approaches negative infinity of g of x is -1. Because it's not going up and to the left forever, and it's not going to come back down, it's going to get awfully close to -1. So the limit as x goes to the left, as the x values decrease, is going to flatten out at -1. Similarly, the limit as x approaches positive infinity of g of x is asking us, where is this graph going as we move to the right forever? Well, it's heading towards this blue line still. So this is also going to be -1, because this blue line represents a function y equals -1. So this is going to get awfully close to -1, but never officially touch it. So the limit as x approaches negative infinity and the limit as x approaches positive infinity are both -1, because as you move to the left and to the right respectively, you are heading towards this dashed blue line that levels out at -1. So the answers, unlike the polynomials, don't have to always be one of the infinities. Now, I don't know how good your eyesight is. Mine's terrible. But you could see that they gave us a nice blue dashed line that lives right here. So we have a horizontal asymptote that seems to cut through regular 4. So the limit, and let's call this h of x, let's give it a name. The limit as x approaches negative infinity of h of x is asking, where is my line going as I move to the left forever? Well, it appears that it's going to get awfully close to this blue dashed line, but never touch it. That blue dashed line happens at 4, and so we could say the limit as x approaches negative infinity of h of x is 4. Similarly, as I go to the right side, as I increase without bound, the limit as x approaches infinity of h of x has this guy leveling out at the same exact blue line. It'll go down, it'll get close to the blue dashed line, but it'll never hit it. Therefore, that answer is also 4. Is there a horizontal asymptote? Yes, there is. Okay, that blue dashed line. If so, write the equation of the horizontal asymptote. Well, like I said before, the equation of a horizontal asymptote is the line y equals a number, and in this case, that number is going to be 4. Now that's graphs. Graphs are great. Let's take a look at it from the point of view of what might appear somewhat on your graphing calculator. Okay, so basically, you have all of these really small numbers, 0, number gets big, big, super big, super big. So basically, -999,999 is basically saying, look, you're going to the left super far. And as you go to the left, you hit this really big number. So this is essentially saying, as you go to the left, you are hitting 4.2, which is 4 and a 2 and 31 zeros attached to it. Listen, I don't have that much money, but that's infinity, or something that's awfully close to it. Okay? So similarly, now our numbers, our t-values are getting bigger. As our t-values are getting bigger, our number all the way over here is getting smaller. So as we move to the right, we are essentially hitting close to negative infinity. Now let's see if that's all we need for now. And we'll go from there. What I'm noticing is there's no undefined thing, so we don't know where this explodes. But that's all right, maybe we don't need it. Find h of 999. Well, that's just simply asking, hey, what happens if I plug in 999? Well, you get negative 478. Find the y-intercept. Well, the y-intercept is when x is 0, or in this case, when t is 0. And when t is 0, you get 32. So the y-intercept is the point 0, 32. Find the limit as t approaches infinity. So that means as I move to the right, which is this guy right here, I am approaching what appears to be negative infinity. Similarly, as t gets smaller, we notice that when t was very small, we had a huge number, so that was positive infinity. These are asking the same exact questions. As t increases without bound, the h of t also increases. Wait, no it doesn't, no it doesn't, no it doesn't, no it doesn't. It's decreasing, it's decreasing, it's decreasing. Ah! Oh, that was close. As t decreases without bound, we're heading towards infinity. That guy increases. All right, much better. That was a close one. All right. Graph each in a graphing calculator and state the end behavior in limit notation. Okay, so we're going to go back and forth, back and forth, back and forth. Let's get our calculator going now. All right, so when we graph these in our graphing calculator, it's important that we wrap anything in parentheses. That's a numerator and a denominator. So parentheses 2x plus 3, close parentheses, divided by x squared minus 4x minus 32. Let's graph that. All right, so we have explosions happening at specific places. It looks like we have an explosion happening at negative 1, 2, 3, negative 4, then 1, 2, 3, all the way over here at what appears to be 8. Now, what I care about is not so much these explosions, I care about the end behavior. Now, what I notice here is that as I move to the left, we're heading right towards the x-axis. As I move to the right, I'm doing the same exact thing. So my end behavior is as the limit approaches negative infinity, I'm going straight to the x-axis, which is 0. And as I'm approaching positive infinity, I'm going straight to the x-axis, which is also 0. So let's go back and state that to the left is 0 and to the right is 0, and they both happen to be the same exact thing. All right, so what we notice here, okay, is again, I'm not going to worry about the stuff in the middle, but that seemed to happen on the left, and that seemed to happen on the right. And as we were moving to the left, as the limit, as x approached negative infinity for f of x, we were heading right towards the x-axis, which is 0. When we were moving to the right, the limit as x approaches regular infinity of f of x was also 0. Now, what we graphed was something where the degree in the numerator was 1 and the degree in the denominator was 2. The degree in the denominator was more than the degree in the numerator, and we happen to go to 0 for both end behaviors. Very interesting. Now, over here, we have a system or a situation where the degree is higher in the numerator than it is in the denominator. Let's see what happens there. Let's go to our calculator and find out. All right, so let's do this again. Okay, in this case, we have a parentheses up here. We have a degree 3, so x to the third, right, minus 3x plus 5. Again, we're focusing on end behavior. That's all that matters in this case, not the explosion stuff. But we're dividing it. We're dividing a cubic divided by a quadratic. So the degree on this one is smaller in the denominator, which is flippy-floppy from what we did before. X squared plus x plus 12, close parentheses. Now let's see what happens here. Ooh, so what we see is as we move to the left, it goes down, and as we move to the right, it goes up. So the limit as you move to the left is negative infinity, and the limit as you move to the right is positive infinity. Let's write that down. Okay, so for this guy, right, I don't care about the stuff in the middle. All I notice is you were going that way and you were going that way. So the limit as x approached positive infinity or negative infinity, I always like to do the negative first, of g of x has me going down, so is negative infinity. And the limit as x approaches positive infinity of g of x was positive infinity. So when the degree was higher in the numerator than the denominator, we appear to have these infinities. Very interesting. Now the degree is the same. So I'm going to go graph that, and we'll find out what happens there. All right, so last one to graph, we have 2, I know it's x, not t, plus 3 divided by x, t. Hit graph. Ooh. Now, we're leveling out. It wasn't like the last one where we go towards an infinity. But it seems to me that if I were to draw a 2 here, and let me do that just to be on the safe side. Let me go down here and see what happens when I put 2. See if that 2 fits snugly in between these guys. Oh, it does. So it seems to me as I move to the left, I am approaching positive 2. And as I move to the right, I'm also approaching positive 2. Interesting. Let's go back and write stuff out. Okay, so what we had with this one, right, is you kind of, I don't remember exactly where things happen. You crept up here and you crept down here. And it seems like right at 2 is where these guys leveled out, at 2. So that would mean that the limit as x approaches negative infinity of h of t is regular 2. And the limit as x approaches positive infinity of h of t is also 2. Interesting how you're a 2. You're technically an invisible 1. I wonder if that has to do with anything. Yeah, I don't know. Maybe. But it looked like here, when the denominator had a higher degree, we hit zeros. When the numerator had a higher degree, we hit infinities. And when the degree was the same, we get 2, which so happens to be 2 over 1. So let's kind of put all of that together and make sense of all this. All right? Rules for end behavior of rational functions. There is a rule here that we don't have to do any math or graph this ever again. If the degree of the denominator is larger than the degree of the numerator, so if the degree of the denominator is larger than the degree of the numerator, so a case like this, right? No matter what, no matter what, no matter what, the limit as x approaches negative infinity is going to be 0. And the limit as x approaches positive infinity is also going to be 0, no matter what. It doesn't matter what these look like at all. If the degree in the denominator is larger than the degree in the numerator, it's going to approach 0. If the degrees of the numerator and the denominator are the same, what happens then? Well, let's just say that you are ax to the nth and you are bx to the nth. Okay, the limit as x approaches negative infinity, what you do is you just say, well, if these are the same, just cut them out and you get a over b. So the limit as x approaches negative infinity is going to be a over b. Similarly, the limit as x approaches positive infinity is also going to be a over b. So in the case where we had in the previous one, it was h of t equals 2t plus 3 over t. I only care about the leading coefficients, and I only care about its coefficients, period. So I don't care about you. I care about the fact that you're a 2 and you're a 1, and we ended up with saying 2 over 1, which is the same as 2, and that's why we got the answer that we got in the previous problem. Now, if the degree of the denominator is smaller than the degree in the numerator, so let's just say you have something like cx to the third over cx squared. Let's make it dx squared. What you're going to do is you're going to plug in whatever infinity you're talking about. Now that's going to be weird, but we would simplify this. So simplify this and say c over dx, because x to the third over x squared is c over dx. And so what we would do is we would plug in whatever infinity that we're talking about. So you would say the limit as x approaches negative infinity of c over d times negative infinity is, I don't care what number that is, anything times negative infinity is going to be negative infinity. Now, if c was a different number, so maybe I shouldn't even write that out. Well, maybe I'll write it out like this. It could be positive or negative infinity. It all depends on what you're doing. Okay, it all depends on what you're doing. If this is 5 over negative 3, then 5 over negative 3 times negative infinity is a double negative and makes it positive. Okay, over here, if I do my math and I do the limit as x approaches positive infinity of c over d, what I do is I plug in positive infinity, and whatever that becomes is going to be my guy there. So simply put, if the degree is higher on the bottom, it's automatically zeros. If they're the same, go to your leading coefficients, turn it into a fraction, that's your guy. If it's higher on the top, then you simplify the leading terms, plug in infinity, and see what you get. So, let's evaluate the following limits. All right, now we only care about leading terms. So when I look at this, you take the leading term of every factor and multiply them together to get 2x squared. Okay, I don't care about anything else. Blah, 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 blah. That's going to be over regular x squared. So I think of the rules that we had up there, and I say the degrees are the same. If the degrees are the same, then you focus only on the leading coefficients, which is a 2 and a 1. You cross these out, and you get 2 over 1. Therefore, the limit as x approaches positive infinity is going to be 2 over 1, which is 2. Coincidentally, the limit as x approaches negative infinity is going to give you the same thing. Now what we have here is we have a degree in the numerator higher than the degree in the denominator. So what you do is you write out 3x cubed over x squared. Okay? You simplify. Again, we only care about the leading terms. So you're dead, you're dead. We simplify that to get the limit as x approaches negative infinity of x cubed over x squared is just 3x. If we plug in negative infinity, we get 3 times negative infinity. 3 times negative infinity is negative infinity. So the limit as x approaches negative infinity of this guy is also going to be negative infinity. All right, let's do a little more. We have x squared over 4x squared, so nothing else matters, nothing else matters, which means you guys have the same exact degree top and the bottom. So when that happens, what you do is you write out x squared over 4x squared, write out the leading terms. You're an invisible 1, so that becomes 1 over 4 after you guys cross out. So both end behaviors are going to level out at 1/4. So the limit as x approaches negative infinity of h of x is going to be 1/4, and the limit as x approaches positive infinity of h of x is also going to be 1/4. So since they're both heading to the same number, that says yes, there is a horizontal asymptote, and that horizontal asymptote is y equals 1/4. Similar things happening here, but now I have two factors on the bottom, so I'm going to multiply those. I only care about the leading term, so my leading term up here is 3n squared. My leading term down here is going to be regular n squared. Oh, they're the same again. So we cross those out and we get 3. So if they're the same, you only care about your leading coefficient. So 3 over 1 just becomes 3. So the limit as x approaches, nope, not x, n. The limit as n approaches negative infinity of g of n is going to be 3. And the limit as n approaches positive infinity of g of n is also going to be 3. And since they both go to 3, that means, yes, we do have a horizontal asymptote. And in that case, it's going to be y equals 3. Okay. Let's do a few problems and call it a day. The function f is given by f of x equals that guy over that guy. Which of the following describes f? So first off, we need to come up with the domain. So in order to come up with the domain, we need to factor the bottom and find out what makes it equal to 0. So x squared plus 5x minus 24 factors out the two numbers that add up to 5 and multiply out to 24. I think we could do x plus 8 and x minus 3. That gives us zeros at x equals negative 8 and x equals 3, positive 3, giving us a domain of negative infinity to negative 8, union, negative 8 to 3, union, 3 to infinity. So not you and not you. The function does not have a horizontal asymptote. Well, we'll see about that. We need to find the horizontal asymptote. You're an x, so the top is x squared. You're an x squared, so you're an x squared. The same exact degree. Simplify them, and you get completely 1. So the limit, okay, the end notation or the end behavior has it flattening out at 1, which means the horizontal asymptote is y equals 1, making B our answer. Okay? Okay. Now we have here a degree that's higher in the numerator than in the denominator. So this is going to be the one that gets us the infinities, which means you're not going to work. So we care about the leading terms of both. And when you have the leading terms of both, you get negative x cubed over 5x squared. Simplify that, remove 2 x's from the top and the bottom, and you are left with just an x on top. On the bottom you have a 5, and you can pull out a negative. So what I'm going to do is, in order to find the limit as x approaches negative infinity, that means we're going to plug in negative infinity into x and see what happens. So negative infinity over 5. Negative infinity is the same thing as positive infinity. Positive infinity divided by 5 is still positive infinity. So the limit as x approaches negative infinity is positive infinity. So we can eliminate some more. Negative infinity goes to negative infinity? Nope. Negative infinity goes to positive infinity? Yup. Negative infinity goes to negative infinity? Nope. Negative infinity goes to positive infinity? Yes. Now let's do this process one more time. The limit as x approaches positive infinity has me plugging in infinity into u. Negative positive infinity over 5 is going to be negative infinity divided by 5 is still just infinity. So the limit as x approaches positive infinity is negative infinity, which is not u, leaving D as my answer. So many Buzz Lightyear jokes that I could do right now, but I just, who has the time? Who has the time? Because, wrong one. So one more. I got ahead of myself. Besides, speaking of those movies, I feel like I'm the only person on the planet who absolutely hates the Toy Story movies. If you disagree with me, comment below. Find the function f of x is defined such that for all x is greater than 0, the line y equals 4 is a horizontal asymptote. So This is all we know. So I don't know what this looks like. It could look like U in blue. It could look like U in purple. Or if you're colorblind, it could look like U in gray or U in gray. But either way, that's all I know. That's all I know. That's all I know. That's all I know. What this means is which of the following must be true. F of 4 is undefined. That means you plug in 4 and you get an explosion. No. F of x can't be 4 for all x. No, that has nothing to do with anything. The limit as x approaches infinity is 0. No, the limit as x approaches infinity of f of x is not 0. In fact, the limit as x approaches infinity of f of x is 4. Plug in 4, you get 0? No. No, come on. I don't know. I mean, it's possible, but I don't know. But having said that, we're done. So as usual, please like and subscribe. That goes a long way for me. I appreciate it. If I were you, I would go back to my YouTube and just type out AP Precalculus 1.7, and that'll take you to these videos here, my random AP Precalculus videos. All right, AP Precalculus 1.7, and watch a bunch of these to help further your understanding. But as usual, thank you guys for watching. Thank you for liking and subscribing. I've been getting a lot of views for these, and I appreciate that. So thanks for everything that you do. Lots of positive comments, too. I always appreciate it. But on that note, full lesson's done. We're just chugging along with Unit 1. Fun stuff. Thanks for watching. Bye.